Good afternoon. Thanks for showing up for the talk. It's nice to see a full room. Let's talk about API security pitfalls. Before we start, let me define what we're going to talk about. So when I mean API, we're talking about typically about a web application. So you have a browser somewhere, you have a server, and you're loading an application. In this case, it's a restaurant application. It's something I use for trainings. It's about posting reviews for restaurants. This application, when it's loaded, doesn't really mean much. It's a blob, it's some HTML, some JavaScript, whatever. If it wants to do something useful, it's going to load data from an API. So it's going to contact an API running maybe on the same system, maybe on a different system. Doesn't matter too much for this image, but essentially it's fetching data from the API, and that's what's going on here. And of course, I show this in a web context, but of course you have mobile applications that do the same thing, you have desktop applications that do the same thing. And of course, you have versions of the mobile and the desktop applications that are actually web applications, even though they don't look like one. So a lot of apps today are Electron apps, which is essentially a very tiny web browser running a web application, even though it looks like a native application. And they can do a lot of awesome things. Why API security? Well, actually, this talk is inspired by the OWASP Top 10 from 2017. I don't know if you're involved in OWASP or followed the story there, but there was a whole controversy when they came out with a new version because people didn't like it. And one of the items that was in there was underprotected APIs. Actually, they kicked it out after the whole controversy in the new version, but it was in there for a reason. And the reason it was in there is because a lot of APIs today are vulnerable. We have a lot of vulnerabilities in APIs. One of the reasons it didn't make the cut is because the vulnerabilities aren't different from what we did before. It's just in a different context. Now we are making vulnerabilities we had in web applications, in mobile apps, and we have them on the API side of things. And that's essentially what this talk is going to be about. If you want to grab the slides, they are on my Twitter feed, so you can grab a copy there. It's a PDF. There's a lot more in the PDF version than what I'm going to show here, because I like to give you more information than I can in a short talk that we have here. Before we dive into details, a small word about myself. Again, you can look at the slide later. Two things I want you to remember. The first thing is I work at a company called Pragmatic Web Security. I founded the company, and I teach developers secure coding techniques. So essentially, I travel the world training developers on how to build secure applications, how to understand security vulnerabilities, and how to prevent making them or making those mistakes in their applications. Second thing is I'm involved in SecOpDev, which is a week-long course in Belgium on security. So we fly in speakers. It's like a conference, but we have 50 people instead of 5,000. And we fly in people from all over the world to teach about secure application development. It's 1 week. It's awesome. If you don't believe me, read the testimonials on the website. People really love it, and you might love it as well. It's next year in March, and that's everything I'm going to say about this here. Let's talk about APIs. Let's set a baseline on API security, and we're going to work on top of that. And the baseline are children's smartwatches. Not very secure children's smartwatches, because Germany actually banned this particular brand in 2017. Germany said, like, what the hell is this? This is in no way a secure product. This is even so unsecure that we don't want to expose children to that, so let's ban it. If you want to read the full article, here's a quote or an excerpt to show you how bad it is. So to give you an idea, the whole idea of this kid's smartwatch is not to tell the time, it's to be able to track your kids in case they're kidnapped. That's what you want to do. However, the API of the smartwatch allowed an attacker to simply show a different location for your kid, which is not what you want if you want to find your kid. So this is a very, very strange setting. The reason I want to talk about this, usually I don't talk about companies that get it wrong, because everybody gets it wrong. Even I make security mistakes. That's just the nature of things. We make mistakes, we fix them, and we learn from them, and we keep moving forward. The reason I want to talk about this, or I don't mind mentioning this, is because after this incident, a year later, they fixed their systems, they updated their systems, and somebody took a look at what's happening there. And they found an API parameter called user grade. And they found out that it had a number like 2 or 3, and they found out if you set it to 1, they had admin access to the API. This is our baseline. This is where we start. If you are banned because of insecure issues, and after a year you still have stuff like this in your API, well, probably you need to find a different business model, but on the other hand, this is our baseline for security. So let's take it from here, and let's talk about some real pitfalls. I'm not even going to spend time on this. Let's talk about another example. I like referring to real-life examples because they show that these things are not as crazy as you might think on first hand. If I show you this on a PowerPoint slide, it's like, oh, come on, who does that? but real people make real mistakes. Here, T-Mobile. T-Mobile has, you can manage your account there, and they refer to your account with a phone number. Makes sense, right? Phone numbers are kind of unique in a system, so why not use that to identify a specific account? So they did that. Somebody figured out if they knew your phone number and they replaced the phone number in the API call with your phone number, they could get your account details. Whoops, not the way things are supposed to go. This is known as an insecure direct object reference, and it's actually a very, very common security vulnerability. It's so common that T-Mobile wasn't the only phone company with this problem. Telefonica in Spain had the same thing. And AT&T in the US had a similar problem. They all suffered from this. And what really happened is that they forgot to implement proper authorization checks. And this is a very simple problem, and if you look at it from a very abstract level, it's very easy, but the way it's introduced is actually not that hard to conceive. Here's an example. Build a Node.js RESTful API in 10 minutes. In 10 minutes, there's not going to be security in there, I can tell you that. And they start with a simple example. Who here has followed a tutorial like this? Many people do. Of course, this is how we learn things. Like, hey, this is how you build an API. Oh, this is interesting, a Tory example. And then, of course, from there on, you learn and you dig deeper and you build out a real application. But look closely here. Read a task, and what you get is you have a find by ID function that accepts a task ID from parameters. There's probably a lot of other things wrong, but there's no check whether you're authenticated. There's no check whether you're authorized, because the example doesn't go that far. It's about the functionality of building the API. You have similar things for deleting a task and so on. And you start with a simple example like this, and then you add authentication. Like, oh yeah, my user should log in. So you implement the whole authentication process, one way or another, doesn't matter. And in the end, you're going to add some checks like, is the user authenticated? Which makes sense, which is what T-Mobile also did in their systems. They checked if you're authenticated. But of course, here you need to think further. You need to think like, oh yeah, I probably also need to check if the user has permission to delete this task. And that becomes a bit tricky, and that's why this is often not explained in detail, because it's very application dependent. How do you decide that? Is the user the owner of a task? Yeah, obviously that's probably something he's allowed to do. But what if you have a team? Or what if you can delegate permissions? Is somebody allowed to delete something that somebody else created? Maybe they can, maybe they can't. So this is always a difficult problem, and that's one of the reasons that these things are often overlooked. And the only way to fix these things is, first of all, write good testing, which is very hard to do, by the way, and go over every endpoint in your API to see, have I checked proper authorization checks? Because if you miss one, you have a serious vulnerability. And that brings us to the first pitfall, the lack of proper authorization. So essentially what you always need to do is you need to check if the user is authenticated, at least for protected endpoints, but also check authorization to have this or to perform this specific operation. It's very, very important. How do you make such a decision? Well, in a web application, what typically happens is the user authenticates once, and then for the rest of the session, is what we used to call it, for the rest of the session you have this authenticated state, and you can use that to make authorization decisions in your application. If you have a traditional web application, you have your browser, you have your backend. Think the PHP era, where you have a simple PHP application with a database, nothing special. You keep some state on the backend to keep track of it, and it works. Is it pretty? Maybe not, especially if you start to scale a bit. You have a few more clients, you have a few more backends, but it works. We implement things like sticky sessions, session replication, whatever you're using, it seems to work. We have done that for 15 to 20 years. Of course, if you build this in an API form, you don't have a REST backend, because REST implies that you're kind of stateless, so you cannot keep state on the server because it's not pretty. Because if you want to scale this up, it's going to be a nightmare. If you have 5,000 backend servers, you're not going to like your job if you have to scale that with server-side state. So we moved to a different paradigm. People said, well, what if we can make this stateless? What if we can keep the state on the client and the backend doesn't need to care about this? We simply get some authorization state from the client and we can perform our checks one way or another. And that's where you actually benefit from a stateless backend. I'm showing you this in detail because to me this is one of the common pitfalls. Many people move towards a system that is completely stateless, which is very hard to implement, by the way, even though they don't need it. If you know that you only have a few thousand users, honestly, I wouldn't go as far as implementing a stateless system. It works fine with the stuff we have been using for 20 years. We know how to do sticky sessions. We know how to do session replication with Redis or whatever. If it works, it works. Of course, you can't call it a pure REST API, but it's still a valid way of doing things, and it doesn't require much effort to invest in a new paradigm of building systems. Of course, if you have the use case for this, this makes perfect sense. But many people come to this realization after they build a system like, why did we do that? We didn't need to do that. And I've talked to people that actually made that realization on their own or during one of my talks. So don't change your session management mechanism or state propagation mechanism or whatever you want to call it for the wrong reasons. Do it for the right reasons. Scalability is a very good reason. Different types of clients that cannot deal with server-side state might also be a good reason. But make sure you have a reason other than build a pure API. Of course, if you plan for scalability in the future, that's also fine. 2 down, a couple more to go. I haven't counted them, so I have no idea how long we have to go, but there's more coming. Back to this image. Server-side state, you keep your session objects on the server. If you've built an application a decade ago, you know about this. This is a PHP session ID with a long string in it, and it refers to a server-side object which contains some state, like user authenticated, true, username Philippe, roles, restaurant owner, or a reviewer, or whatever. What changes is if you push this to the client, if you build your stateless API, you're actually pushing that information to the client. Nothing on the backend, you can spin up as many backends on AWS as you want, as long as your credit card can actually pay the bill afterwards. Very easy on PowerPoint. Seriously, it's just dragging the little things around and you're done. In reality, it's much more complicated. In reality, you're changing an entire paradigm. Because data that used to be trusted on the back end now lives on the front end. And we all know that something that lives on the front end cannot be trusted. That's the inherent nature of pushing stuff to the client. How do you do this in practice? What vehicle do you use to actually encode that data? Today, chances are that you're using a JSON Web Token, a JOT. A JSON Web Token looks like this very big blob of data. In reality, you don't get fancy colors. This is the jot.io website that decodes it. In reality, it just looks like a very long string with dots in it. There's a dot here and a dot here somewhere that separates the different parts of a jot. And a jot contains some header information, metadata essentially, and it contains this purple part here. That's the interesting part. That's the data. And there you can see here, it's a very simple, straightforward example. We push some user identification information to the client and some roles which we will later use for authorization. So whenever we push this to the client, we get this back at the server. So what do we do now? We actually have to use that information. So here's a Java example of getting the information out of a jot. So you get your token from somewhere from the client. I'm going to talk about that in a second. And then we decode that and we use whatever is in there. So you can now say jot.getClaim roles. Oh yeah, it has the restaurant owner role, so this is good. We can perform this operation. Sounds like a good idea. Well, if you build code like this, you probably should have read a bit more documentation, because the decode function is not the way to do this. What you should have done instead is write more code, because more code in this case means better code. What's happening here is this is decoding only. But if you decode only, you simply take the data and you handle that. But a jot comes from the client. You cannot trust it. You need to verify whether it has been tampered with or not before you can use that data. And in a jot, we do that with a signature. So what you actually have to do is you have to take that jot, you have to verify the signature that has previously been generated, and if that signature is valid, then you can trust the data in there, because then it must have come from a trusted resource. And that's essentially what you need to do. So misusing an API, like the decode API, can result in a serious vulnerability in your application. And some people actually have that. Because from a functional perspective, it works. You get the data, and every positive unit test will actually succeed, because the data is valid and you can use that data. However, if somebody gives you invalid data, a token crafted by the attacker, you are in trouble. That brings you here. Mishandling this client-side session data. And if you're not using JOTs but something custom, the same principle applies. You need to have a signature in place to protect the integrity of the data. And by the way, if you're storing sensitive stuff in there, you also need confidentiality. You need to encrypt that token. Many JOT libraries have built-in support for encryption as well. Back to our fancy colored JOT. You have this signature here. The signature is the blue part. The signature actually is, well, the signature is generated over the header and the payload. So the header and the payload are protected using that signature. You can see here that it's using an HMAC. I'm going to show you an example in the next slide what that means. You also see this super secret HMAC key. That is your secret key, which you should not put on PowerPoint slides, and it should not be super secret HMAC key. Just to be clear, it's not a good practice to do that. How does it work? How does an HMAC-based signature work in practice? Well, you have your data that you want to protect, header and payload in the JOT case. And what you're doing is you're using an HMAC function. Don't write your own thing. Don't come up with your own crazy crypto ID. Use a proper HMAC function from a proper library. And that HMAC function is going to ask for two inputs, the data and a secret key. So you give it to it, and it spits out this HMAC value. It's going to look like a hash, but it's not a plain hash, it's an actual HMAC. And that is what you push to the client along with the data, but the JOT library does the whole thing for you. But that's essentially what's going on under the hood. How do you verify that? When it comes back, the client is going to give you the data and the signature, and you're going to run the HMAC thing again. Well, the library is going to do that for you, but essentially the HMAC algorithm is run again with the data and the key as input, and out comes the signature. And they can be compared, and if they are the same, then you know that the inputs to the HMAC function were the same as before, meaning that the data here was the same as the data here, and that you can trust it. If they differ, well, something has gone wrong, so either the data or the key have changed, but if you're using the same key, then the data must have changed, so we don't want it anymore. Somebody has changed something in the data. Might be a white space, we don't care. We don't care what has changed, we just care that it has changed and we kick it out. Never ever accept that. Awesome. Good security, right? I see people looking skeptical. Well, this is the most known scheme for signing JOTs. This works really well for one application. Generate tokens, give them out, get them back, verify. Solid. But what if you have two applications? What if you get a token from Google? You can ask Google, like, hey, can I get your HMAC secret so I can verify that token? And Google is going to be like, well, you probably won't even get a response, but otherwise they're going to be like, no, go away. Why? Because once you have this secret, it's the same secret for generating signatures and verifying signatures. So anyone who has this for verifying can generate arbitrary tokens. So you should never, ever, ever share this secret with anyone else. Not even between two applications that you control. Because there's a better mechanism, and it's an asymmetric signature. What you should be doing is, in that scenario, is you should use a different way of signing the JOT, RSA in this case. So essentially you have the data, and you have a private key, and you feed that into a signature algorithm, an RSA algorithm. I'm not going to open it up because different algorithms use different ways of signing. It doesn't matter. The library handles this for you because out comes a signature. And that signature, you push that to the client along with the data. And it comes back, and you have to verify this. And what do you do then? Well, you use the library again. You feed it the signature and the data along with the public key. And the library is going to say true or false, or no exception, exception, whatever implementation strategy they follow. And if it's green, it means that the data and the signature belong together, and they have been generated with a private key that belongs to this public key. And if they don't, if you get an error or whatever, that means that something is wrong. You don't care what, you simply reject that token. And this looks a lot better now, because now you have a service, one service can generate arbitrary amount of tokens, and anyone with a public key can verify them. This is exactly what we use in things like OpenID Connect. If you choose login with Google, the application you're logging into with Google gets a token from Google saying this is philippe@gmail.com with this very long unique identifier. And Google signs that with their private key, and your application has Google's public key. Everybody in the world can have Google's public key, and they can verify the validity of that token. So they can trust that it comes from Google and that the data actually is legitimate, that the integrity is guaranteed. And that's very important. Don't misuse the JOT signature scheme. I've heard people advise to share the secret with different applications or even different parties. Never do that. The moment you have a multi-application scenario or a multi-service scenario, you need to use asymmetric signatures and keep that private key private. All right. So far, so good. Well, if you're using crypto, it's probably never that simple. And it never is. Because if you're using signatures like this, you need to have thought about a few things, like key rotation. You cannot use one key for your entire application lifetime unless you build applications that only live for a day or something. You need to rotate. And that depends on how much or frequently you use the key. Sometimes you need to rotate the key daily, weekly, monthly, whatever. But if you rotate a key, you essentially generate a new one to start using. But if you get a token with the old key, how do you know which key was used? Because it will not verify if you have a different key now. And that poses some challenging problems. And this is something that not a lot of people talk about. But JOT actually has a few mechanisms to manage keys or to help you manage keys. The simplest mechanism is you can include a key identifier in a JOT token. You can add a KID with a string-based value. What that string is up to you. You can call your keys Monday, Tuesday, Wednesday, Thursday, Friday, Saturday, Sunday, if you want to. I don't recommend this, but you can do that. Why not? And then in your token, refer to, oh yeah, this was signed by this specific key, and when you get it back, you can look up that specific key, and you can verify the signature. Of course, this works well if you have control of the keys, if you can actually fetch them with an ID. In a more complicated setup, in an OpenID example, for example, you might consider using key URLs. So here's an example of how to generate a signature with a key URL. So you can tell the receiver, by the way, you can get the keys from restogate.com/jwks.json. It's a JSON format to specify public keys. It's not pretty, but it kind of works. It's so elaborate, I cannot put it on a slide, by the way, but look up the spec if you want to see examples of JSON-based key specifications, and you'll know what they look like. But you need to think about these things, and many people start using JOTs without properly thinking this through. And if you have a lack of key management, you're going to run into problems sooner or later. So you need to think about this upfront. How will I manage keys? Who will generate my keys? Where will I store them? How will I get the public keys? How do I know whether I can trust the public keys? And I know I've been a bit light on details because I want to cover other topics as well, but there's a blog post, which I'm going to tweet about after the talk, that explains this in more detail. But if you Google JOT and my name, you'll find it. It's on the internet, and it's pretty easy to find. All right. Let's talk about something else now. So we talked about representing data, server-side session object, JOTs. But how do we get that data to the server, from the client to the server? Well, the very traditional way of doing that is with a cookie. So if you have a PHP session ID or a more generic ID, it's essentially a number or an identifier. You add it in a cookie, and the browser will send it out on request to the server. Server grabs that identifier, looks up the session object, and off you go. With JOTs, we don't like that. With JOTs, people were like, yes, we can finally get rid of cookies. Let's do it. Let's use the authorization header instead. And that's exactly what people are doing. So typically in an application like that, you're running a front-end application, like let's say an Angular app or a mobile app, and you're adding an authorization header yourself in code with the type bearer and your JOT token as part of that header. That's why people often talk about cookies versus tokens, even though the comparison doesn't really make sense. Why doesn't it make sense? Because why not add a JOT in a cookie or an ID in an authorization header? You can. Both accept string-based data. And while this seems crazy, like, oh, come on, whoever puts an identifier in an authorization, no, we don't do that. No, we're not going to put our PHP session ID in there. But other identifiers, maybe. If you're using OAuth, in OAuth you have two types of tokens. You have a reference token, which is essentially an identifier, which is often put in an authorization header, and you have a self-contained token, which is a JOT, which is the data in itself. And the reference token needs to be resolved with the authorization server to get the data that belongs to that identifier. So this is not as uncommon as you might think, even though it looks a bit ridiculous on this slide. Why does this matter? Because we're building web applications. We're contacting an API from a web application, a mobile, a web view, an Electron app, or whatever. And cookies actually work really well with the web. And custom headers, maybe. Let me put them side by side. First of all, cookies and the authorization header, they can both contain anything you want. Any string-based data can be put in the headers, so there's no restriction to put a token in an authorization header and not in a cookie. Cookies work really well with a single domain. If you are running an API on one domain instead of different domains, cookies actually work well. The authorization header, on the other hand, can be sent to any domain you want. So if you have multiple domains, cookies are going to be a real pain, and the authorization header is going to work pretty nicely. But why would you choose cookies over the authorization header? Because cookies are ugly. Well, cookies are handled automatically by the browser, while the authorization header is not. So this means that if you want to use the authorization header, you'll have to write custom code. You'll have to write code to get that from a response from the server, store it somewhere in the browser, get it again from storage in the browser, and add it to outgoing requests. If you're building something like an Angular app, this is code you have to write. No app handles this automatically. And if you have to write code, you have the possibility to introduce security problems, which people are doing in practice. A second advantage of cookies, like I said, cookies work really well with the web. cookies are present on every request leaving the browser, including DOM-generated requests. If you're loading an image tag, the browser will add a cookie. If you're loading a script with a script tag, the browser will add a cookie. Your authorization header will not be there. If you're opening a WebSocket connection, the browser will add a cookie if one is present. But your authorization header is not there. Why? Because you do new WebSocket. This is not a request that is seen by your Angular application. This is something generated from the browser's internals. And I've seen people building an application with the authorization header, and then after they build their whole authorization system, they're like, oh yeah, we also need authorization on this loading of the image here. Oh, crap. We have no authorization header. And they built like a complementary cookie-based mechanism to overcome this hurdle and make sure that they could get some information there. And that's a lot of pain you could have avoided by thinking about these things up front. So don't underestimate this session transport or this authorization state transport. Cookies are, I know they're ugly. I'm not going to talk about cookies any further because I can talk about cookies for hours. You have cookie attributes and cookie prefixes, and it's a nightmare. But they are inherent to the web. Well, people are working on getting rid of them once and for all, but it's going to take a while. It's called the HTTP state mechanism. Look it up. It's actually quite an interesting proposal. But for now, cookies are the only thing that works well with the web. So if you need these features, cookies are probably more useful than a custom authorization header. Of course, if you don't need them, the authorization header is also solid. One of the drawbacks of cookies is an attack called Crosssite request forgery. People tricking the browser into sending a request, the cookie will be there, and the backend is like, ooh, a cookie. Oh yeah, you're Philippe. Boom. Review created, which is a problem. I'm not going to talk about CSRF details either, because in an API world, if you're doing it right, CSRF is a bit less of a problem. Because if you're sending API requests from XHR, you're probably not going to send web requests, not form-encoded data. Instead, you're probably going to use something like application/JSON as a content type. And if you're sending requests with an application/JSON content type from a different origin with XHR, the browser is going to add this origin header to the outgoing request. The browser is going to tell the backend, hey man, I'm sending a request from https://maliciousfood.com. What do you think about that? Actually, this is an option. This is not a real request. The browser is asking the server, I'm about to send you a put request. What do you think? Good? Bad? And the server, if the server actually expects this, he will reply, yeah, sure, I know these guys. Give it to me. That's good. If the server has no clue who malicious food is, he's probably not going to reply, sure, send it. The server is going to say nothing at all, and the browser is like, oh, my mistake, I'm not going to send this. And this is called cross-origin resource sharing. And the pitfall here is the fact that you fail to enforce a strict CORS policy. But if you have a good CORS policy, if you force the use of CORS by using an application/JSON content type, then your application or your CORS policy will automatically protect against cross-site request forgery as well. So that's an added benefit of proper API design. One pitfall here is if you implement CORS support yourself, you're opening yourself up to make mistakes. That's security code you're writing yourself to check the value of the origin header. And I can't tell you how many applications use a variety of one of these code lines to check the value of the origin header. And I see someone laughing here at the front row. And on PowerPoint, again, it's like, oh, come on. No, we don't do that. But in practice, we do. This is an example I got from a presentation I saw a couple of years ago, where this vulnerability exists in a Bitcoin wallet system. They had an endpoint giving out access tokens, and their CORS policy was wide open. So anyone could grab an access token for your wallet from your browser and actually steal your crypto coins. 2 years ago, that probably wasn't that big of a problem. Today, that's $1 million problem if they can do that. And we see attacks against these systems over and over. So what's the problem here? Well, what if I send a request from restaurate.com.maliciousfood.com? That's going to match 2 out of 3 of these code patterns. Or from maliciousrestaurate.com. That's also going to match a few of these. And these things are, again, quite common. And to make it even worse, there's a product. I don't remember the name of the product. I just Googled this, and I found it like the 3rd hit or something. That tells you to configure your Apache server like this. This is an on-premise thing. You install it on your web service, and you have to configure your Apache. And you say, like, just add this to the config, and you're good to go. Our product will work. But look at this. This is the origin header. They're reading the origin header from the request and storing this in a variable and putting that back into the outgoing header. I'm going to save you the details, but if you know how course works, the red parts here are really problematic. Essentially what they're doing is anyone can send us a request. We'll accept it and reply to it, even worse. And oh, by the way, you're also allowed to use cookies with that request, so we are sure we can authorize you. This is a wide open course policy and one of the worst configurations ever. Because the creators of course, they saw this coming. They saw people coming and said like, people are going to use a wide open policy anyway, so let's use a wildcard and let's provide a wildcard. And they have a wildcard, but the wildcard cannot be used with cookies because they said that's a bad thing. And then of course people found a way around this anyway. Like I said, I'm not going to name the product. I don't like shaming them, but be careful if somebody tells you to add something like this to your configurations. And this brings us to the failure to configure or implement course correctly. Today, this is less of a problem because many frameworks today have built-in support for course policies. You can configure them through XML or through code-based configuration. You can actually provide the framework with the configuration parameters and it will enforce that policy for you. But there are many custom systems out there that suffer from these vulnerabilities. All right. So we went pretty deep into course now, cross-origin traffic. There's some low-hanging fruit I haven't plucked yet. Things you might be wondering, like, why isn't he talking about something like input validation? Should your API accept inputs like this? That looks a bit funky. Here, probably no. /user/1 with some crap behind it. Should probably be a number-based input, so it should never ever accept something that is a string. It's also SQL injection, if you recognize this, not a good thing. So lack of input validation is also a common problem. You should always input validate. It's so important. There's a reason I didn't start with that. And the reason is that input validation will never protect you. Input validation is a good first line of defense, but it's not a primary defense. Input validation, I like to call it to keep the crazy out. If you know upfront that the data is invalid, kick it out. But sometimes you're going to get data that looks crazy, but actually really isn't. Look at this email address. What the hell is that? This is SQL injection, right? If this ends up in a SQL query, you're in trouble. But this is a valid email address. Depends on who you ask, but RFC-wise, yes, this is a valid email address. So this will pass any validation checks based on the RFC for email address. This is an actual valid email address. I cannot create it because my provider doesn't think it is valid, but it's supposed to be valid. And this shows you that input validation is a good primary first line of defense, but not a primary defense, because valid data can cause problems. And that's why we usually focus on output defenses, parameterized queries for SQL, output encoding for cross-site scripting, because input validation can help, but will never be a primary defense. It will never be the only defense, or it should never be the only defense. All right. And then eventually things go wrong. Perfect use of the very nice emoji here. What happens when things go wrong? That brings me to the final pitfall, the failure to compartmentalize. Today we still build monolithic applications. We still build APIs handling public operations and private operations. We still build front ends handling public and private stuff, meaning that if something goes wrong in one place, in a very unimportant public page, it might affect all the private stuff as well. And what we need to be doing in web applications is split these things out. We have something called origin-based isolation in the browser. If you run your public stuff on www.restrograde.com and your account management on accounts.restrograde.com, the browser will keep them separate. And if something goes wrong in one location, it will not automatically affect the other locations. It might spread, but it's going to be a hell of a lot harder to do that. And that is a very important message to realize. And that is something we should start thinking about. There's no reason to have authentication mixed in with the rest of the application. Split it out. Whether you use a very simple isolation mechanism or something more complex like OpenID Connect, I'm going to leave that up to you. But we need to start thinking about compartmentalizing these things. So my takeaway here is question everything. Security is a lot about knowledge, but mainly about a mindset. It's about questioning things. Do we know what we're doing here? Do we really need this? hey, this is super cool. Are we really going to use this JavaScript framework from 1 week ago? Maybe we wait a few versions. It's these questions that help you. And whenever you don't know the answer to the question, you need to find someone who knows, or you need to do some research. And it's okay to say, I don't know. That's the whole point. It's not okay to say, like, I have no idea, but it's probably going to be okay, deploy. It's probably not. Maybe it is, maybe it isn't. But seriously, talk to a security person in your company, talk to someone in the security team. And if they don't know, they should escalate as well. If you're implementing crypto and you have no idea what you're doing, hire a crypto expert to help you. These people know, these people know, and they can actually help you build secure things. To help you, there's a lot of stuff you need to question, like, do we have this and this and this? We saw a few examples with Jot. To help you, I built some cheat sheets. So these are cheat sheets about Angular security and JSON Web Tokens that actually have a checklist of things you can see. I know that the previous talk didn't like checklists, but this actually helps you in combination with other things, of course. I'm working on a third one on API authentication, but that's not out for a couple of months probably. All right, thank you very much for listening. Sorry, yeah, they're on my Twitter feed as well, so it's very easy to find. Once you look for pragmatic web security, you can easily find the cheat sheets, my Twitter feed, some recorded talks about other topics, and so on. Thank you for listening. Thank you for staying. And if you have any questions, we can maybe handle one now.